Hi, I'm Pat McGarry, the VP of Engineering at BlackLynx. In this demonstration, we'll leverage the power of the BlackLynx software framework running on a single off-the-shelf Dell server to perform a computationally complex edit distance text analytics operation on a rather large 20 plus gigabyte raw data set with no extract, transform, or load, often called ETL, operations applied, and no pre-indexing performed without any caching whatsoever. We'll demonstrate the edit distance acceleration for both CPU-only acceleration as well as FPGA-based acceleration, both in seamless fashion and both powered by the BlackLynx software framework. Before we begin, allow me to define edit distance for those that may be less familiar with it. Edit distance is a measure of similarity between two strings, two sets of bytes, given the number of character changes, character additions, and character removals needed to change one string of bytes into a second string of bytes. It is therefore quite useful for a variety of search engine technologies when misspellings or varying differences in words, numbers, various character sequences to include complex things like DNA sequences, and similar things need to be quantified. Edit distance is a great fuzzy searching tool, but it is not often used since it is typically very difficult to implement efficiently for useful distance values larger than about 2. At BlackLynx, we've created novel ways of vastly improving the speed of edit distance for arbitrarily large distance values, as well as several other classically difficult algorithmic problems in addition to edit distance, without requiring any special ETL or indexing operations by leveraging a powerful acceleration parallelization framework that we've built. And that allows us to achieve on the order of 1 to 2 orders of magnitude performance above and beyond traditional software means. Before we jump in and look at BlackLynx acceleration of edit distance, let's first look at a widely used open source alternative that solves the problem. It's called Tray-agrep, albeit it solves it in extremely slow fashion. I've pre-run this example and you can see the output here on the screen, and it took over an hour to complete against a 21 gigabyte data set. And just to show you that that is indeed the size of the data set, let's go ahead and show you the data. You can see here it reports as 22 gigabytes from Linux, and the full byte size is shown right there as well. You can read all those numbers off. Now, this input corpus that we used was actually a snapshot of the Wikipedia corpus taken from around May of 2015. And the open source Tray-agrep tool that we used is easily installed on a variety of Linux distributions, including the Ubuntu 16.04 LTS distro that I'm running on this system, and you can see that here, right there. And what's important there is that this means that you can easily run this tool on your own and see its performance yourself on this large data set or other data sets like it. Again, there's nothing special about the data set. It's just directly pulled from Wikipedia as a text dump back in May of 2015. In our edit distance acceleration example, we'll be using a BlackLynx command line tool called RiftX that wraps to our open APIs. If you're interested, details of all of our APIs, all of which are open, are easily referenced on our website at www.blacklynx.tech. That's a .tech extension /API, as you can see here in the address bar of my Firefox browser. And the one that wraps to our RiftX command line describes our C, C++, Python, and Java APIs is this one right here. It's called the Rift Open API Library User Guide. You can click on it here to download it. You do not have to be a customer. You do not have to log in. Or you can, of course, preview it in your browser. It's just a PDF file. Okay, now we are back at the terminal that we just finished up the Tray-agrep operation on. And the first thing I'm going to show you is that this machine has an awful lot of RAM on it. But you'll notice that the entire corpus, after it was run by Tray-agrep, was cached at 21 gigabytes. So to level set, since we don't require any caching whatsoever to get extraordinarily good performance, we're going to clear that out. So I have a simple little utility called clear page cache that I wrote that clears out the page cache. And now you can see the memory clearly shows that it is cleared out, and that buffer is no longer, 21 gigabytes is no longer cached in the system. And with that, I'm going to paste in the RiftX command line that we're going to be using. And I'm going to let this start running, and I'll be describing the parameters here shortly. But before I do, I want to show you, moving over to that system, an HTOP report so that you can see that we are slamming those CPUs right now because we told it to run in all CPU mode, and there it goes. So I'm going to go ahead and quit that and actually walk you through now the command line parameters. So the -v operation just says show us some verbosity when you're done, like the number of results. It should match the 1690 that we saw with tray agrep. It'll also give you things like the data rate. The -f is just the input file corpus. You can have as many -f parameters as you want, and we also accept Linux file masks. Any Linux standard file is fair game. Here, of course, we're using the same exact corpus that we used for our tray agrep benchmark up here. -s is our query search operation, and it's told to use a raw text contain search, which is basically saying treat it as a string of binary bytes and run an edit distance operation in there looking for Sylvester Stallone, spelled horribly wrong the same way we did up here with tray agrep. A distance of 4, so that should find all the regular spellings of Sylvester Stallone and then some. Return context in lines. This is interesting because we won't just return the results, but we'll return the full line that contain those results, which can be useful for downstream natural language processing or other tools. We'll create the output data in a standard Linux file in the /temp file system. It'll be called foo.txt. It can go anywhere and be anything. And finally, we've told it to not be so smart. We've told it don't query the hardware, don't optimize based on the available compute. Instead, just do it in pure software, pure CPU, and get the result. Now, the full operation for this version of this CPU acceleration takes about 2 minutes and 20 some odd seconds. So now we'll sit here and wait for it to complete. So here we finished the operation, and you can see we finished in 2 minutes and 25 seconds, compared to the 66 minutes that the open source tray agrep solution took on the same hardware. If you do the quick math in your head, that's around 28 times better performance running our tool in CPU only mode without any other special acceleration than the open source tool is able to accomplish. I think you'll agree that that's a heck of a performance improvement just running in CPU alone. One other interesting thing here is that since this is just a standard Linux output file, we can look at it with standard Linux tools. So you can actually look at the file and say it's 1.9 megabytes or so in size, and you can head the first few lines of the file. And sure enough, if you look here, you'll see that there is Sylvester Stallone that it found in this particular sentence. And if you look up further, you'll see similar kinds of things in the other blocks of line data that was returned. Okay, so now I'm going to use my up arrow key and go back to my riftx command that we had just typed, or pasted in I should say. I'm going to delete that last parameter that told it to be dumb. Now it's going to be really smart. Now it's going to, in real time at runtime, query the available hardware resources on the server that we're on and decide how best to run the algorithm that was requested. In this case, it's going to determine that there's an FPGA available. And so it will route the appropriate portions of the edit distance algorithm to the FPGA for the parts that it can parallelize and excel at. And it'll do the rest in CPU fabric. So I'm going to hit return here and start this operation. And just like last time, I'm going to first show you a CPU HTOP report. And you're going to notice something extremely interesting. There's lots of processes running, but extraordinarily little CPU activity. That's because the vast majority of the effort is being able to be handled by the FPGA, by the intelligent BlackLynx framework running as riftx. So I'm going to quit the HTOP and come back over here now and just wait for this to finish. This will finish in under 30 seconds typically. And there it goes. Finishes in under 29 seconds. Now this is not by accident. This is because the FPGA is able to trivially parallelize large portions of the algorithm, and we figured out ways to ensure that those pipelines stay busy in between CPU operations. And that's one of the things that BlackLynx excels at. We're able to take very complicated algorithms and correctly route the CPU portions, the FPGA portions, and in certain cases even the GPU portions to the right hardware at the right time to get the best possible performance, the lowest possible power. And you can see we found the same numbers of results in under 30 seconds, same data set, everything else was identical. And you also can probably figure out at this point that the user didn't have to know anything about FPGAs to make this work. They just said, hey tool, go do your job, and it did it on its own. I'll also use my up arrow key here and show you that this file was indeed just now generated. And in the same way, I can head the output here from the FPGA just like I could from the CPU. It's the same exact output. Nothing has changed. Here again is Sylvester Stallone in the output files. This chart helps to summarize what we've demonstrated. And what we showed was using the common tray agrep tool, took about 66 minutes, and it doesn't scale. You can't actually parallelize that particular operation. It wasn't built for it. So there's no way to get computation-specific numbers to get to a 30-second goal. In our CPU-only acceleration paradigm, we showed us finishing in our example of 2 minutes and 25 seconds. And when optimized, you can get that to around the 2 minutes and 20 seconds you see reported here. Now, to get that down to 30 seconds or lower, you would need 5 servers data sharded. And if you do all the computation-specific power measurements like we've done in our lab, you're well over 2,000 watts to solve that problem. And so we're just arbitrarily giving that the 1x performance number, given our acceleration paradigms. And again, we believe that we have the fastest CPU accelerated at a distance in the world. And if someone's got a faster one, I'd love to see it. But now when you plug the FPGA in, we showed that we were able to get our duration down to under 30 seconds. And we only needed 1 server to do that. And the FPGA computation power measured at the input of the device for the FPGA portion was only 16 watts. And doing the math there with the time and watt calculations shows you that your performance per watt advantage, using only a single server to reach that goal, is over 100x. And that gives you the best possible performance at the lowest possible power, which becomes an excellent paradigm, an excellent architecture and platform to use, especially at the edge of networks, where you've got to make quick decisions on newly arriving or newly sensed data without relying on lengthy backhaul, lengthy ETL, lengthy indexing operations, which just slow your ability to make decisions fast. I hope you found this demonstration useful. For more information about this use case and the rest of our impressive line of compute acceleration products and capabilities, I encourage you to visit our website at blacklynx.tech. Thank you very much.